I think we really have to appreciate just what an achievement it is for an organization like this to exist for 10 years, but still be going strong, you know. When I'm going around the world, people are saying to me, oh, your Nanocem thing, when is this finishing? I said, no, it's not finishing. It's going on and from strength to strength. And I think this is very important because over the years, we've really evolved our ways of doing things. Nanocem is much more than we can present to you in a few presentations at an open meeting like this. Other things are featured in the posters, and I hope you'll have the opportunity, particularly in the coffee and lunch breaks, to have a good look at the posters and discuss that with some of the people. You know, what we're going to present, as I emphasize, is really just the very small part of things. So I just want to give a little bit of background how we got here. I came and started work on cement in 1980. That was when I started my PhD. And I hope it was a total coincidence, but this was just the period when all the big labs were closing down. You know, I was in the UK and we had British Cement Association. In France, they had big labs at Cyril. In US, they had big labs at PCA. And at the end of the 1970s, all of the people decided, well, what are we getting from these big labs? You know, what are they doing? Why are they here? So they tended to be shut down. And as with a industry that's quite slow moving, nobody really noticed anything for quite a number of years. But then we find that the work that's going on in universities is getting more and more fragmented. You have some small isolated groups, but there's a lot of duplication. This is particularly important, what we see in a European context. You know, people are doing a PhD on something for 3 years and then they stop and they start on something else. And really, I think that, you know, by the time we were looking at Nanocem, we were realizing this situation had to change. And for me personally, this was very important because I was first of all working in a university up until 1995. And then I had this opportunity to go and work for Lafarge, which was a fantastic opportunity, because I said to myself at the time, you know, it's great being in a university, publishing these papers, but what's the point? And I need to know what the point is. And I spent 6 very interesting years in Lafarge. This was a time when Lafarge was really reorganizing and redynamizing their research. And I learned an awful lot about why research was needed, why it was important. And what I wanted to do when I came back to EPFL was really say, okay, I'm not going to go back to being in an ivory tower. This has to change. And fortunately, when I went around Europe and met people like Wolfgang and like Marcus and like Jesper, who are here today, and said to them, you know, I think we should group together and make this organization, they said yes, and I was quite surprised. I was really not expecting that, but I think it was the right time because what we're facing now, as Philippe Gillet said, is a lot of challenges. A lot of challenges to do with environmental pressures, but also now we're seeing more and more pressures just due to demand. The demand for cement is really skyrocketing, as we've seen in China, and it's not even clear how we're going to be able to satisfy this demand. So, to cut a long story short, in May 2002, we had our first meeting of 6 partners in Paris. We made a bid for an EU network of excellence. This wasn't successful, but I think this was actually the saving of Nanocem, because I think if we'd been sucked into an EU system with a scientific officer telling us how we had to run our own governance, this would have not gone very far. I think the real success was that we realized this was needed and we could do it independently. And then it took us about another year to sign the consortium agreement. So when we were deciding, well, when's the 10 years, we decided, okay, the signing of the consortium agreement, this is like, you know, the bit before was like the pregnancy, and now we're giving birth to this consortium. So now we have a large number of industrial partners, mainly cement producers and also admixture producers. last year we accepted our first member from outside Europe, which we're very pleased about, to welcome Siam Cement Group, SCG. And we hope they will be the first of several companies coming from outside Europe, really, because we know that the industry is now international. And these industrial companies, we have also the academic groups, and I mean, you know, for me as an academic myself, I've been frankly amazed at the impact this consortium has had on the other academic groups. Because most of the academic groups at any one time will actually not be receiving any money from Nanocem. It's not like the industrial people put money in and then it goes to all the academic partners. Most of the academic partners are financing their own participation, and in fact, it's an obligation on the academic partners that they have to contribute their own independent research. Nevertheless, we have people queuing up at the door, knocking at the door to try and join because they realize the benefits of being integrated into this group and really having the possibility to focus on what the big issues. So this is an industrial academic partnership, and these two words are key. First of all, partnership, that it's not the industrial people just funding the academics. It's really the academics are also absolutely fundamental. And that word fundamental is important because this is how the different industrial companies can work together. And really this realization that no one company can ever possibly start to solve these big questions like what's the structure of calcium silicate hydrate and things like that, but together we're going a long way down that line. I mean, the progress we've made in terms of real answers is quite unbelievable. So the industrial partners contribute euros for core research programs. The academic partners contribute research projects. And we aim to really foster this dialogue so that the industry is really giving a perspective on what, from a practical point of view, are the areas where we need better understanding. And the academia is working on these and also interpreting these, because it's not enough to do some nice research and publish it in some erudite magazine like Nature or PhysRev, because this will have absolutely zero impact on the industry. And it's not, it's not even just telling the industry, oh, we did this. You have to be in constant dialogue to try and explain and interpret, and this is something that really goes both ways. So I see this as a process of, continuous scientific debate. Nanocem has 2 main consortium meetings a year, but this is just the tip of the iceberg. In parallel with these 2 main meetings, there are multiple meetings from a size of 3 or 4 people to 10 or 20 people on specialist workshops. Typically, we're organizing around 20 events a year. So this is like, 1 every other week on average. So it's a very active network, and constantly we're debating what are the key questions. Because there's so much to do, if we don't focus our effort on the key questions, then we cannot have effect. And the structuring effect this has on research then has an impact way beyond what is funded by the new industrial money. Because it helps the academic partners to make joint applications to EU programs, to even make their own applications to national funding bodies. I mean, for example, Paul and myself just got a funding from the Swiss National Research Council from a subject that's directly coming out of the core project that Nanocem funded a few years ago. So why do we need this research? Well, we need this research to address the problem of growing demand. And, we could probably notice here that, in fact, Europe is not predicted to have any growth in cement. But this is, not the point, because, we're part of a worldwide community. CO2 is a worldwide problem, and most of the industrial companies here have the majority of their applications outside Europe. So even though they're European companies, they're really actors on the world stage. And we have to be able to develop technologies which will enable, for example, India, which is seeking to develop in the same way that China has done over the last 10 years. This will need a tremendous amount of cement. India has a huge shortage of limestone. They think they only have enough limestone for the next 20 years for building new cement plants. The existing plants, they have more, but for new plants, maybe as little as 20 years. So we have to find solutions to make that limestone go further. And how can we do that? Well, I think we all know in this room that the most successful way to do that is to blend Portland cement clinker with other materials. So Portland cement clinker is a really, really underappreciated product. You know, I mean, I really want to say this to people in this room, that Portland cement is an incredible product. It's really optimized as far as the geology of the earth, as far as the energy of production, and the price. I mean, it's such a bargain. So let's not sort of say we're going to seek for some miracle, because we live on the earth, we have only the elements that are in the earth, we're not going to be able to change that. And so the most promising route to tackling this issue both of CO2 and of increasing demand is supplementary cementitious materials. Of course, here we have, and this has been very successful over the years, as illustrated by these figures from Holcim, but in fact we don't have huge amounts of these materials. So I managed finally to update this graph of Jespers with modern day figures, that now the amount of cement produced is getting close to 4 billion tons. The amount of slag is maybe 5 to 10% of that. So it's great, we can put 70% blended slag in a cement, and it works no problem from a technical point of view, but we're not going to be able to do that on any scale worldwide. Fly ash, there's quite a bit more, but much of it is really low quality and not very suitable. So we have to look for new solutions, as we're doing for with limestone, our particular thing of calcined clay, and I'm not going to monopolize the presentation on this, but this gives very exciting results at early ages. But this is just one example of many solutions. So I think the main fundamental message is there's no one magic bullet solution. There are many, many solutions. And that's why the research we need is fundamental. Because if we've targeted on a specific application by application, we spend ages and ages, you know, optimizing each individual solution, where to face the problem we're going to have to know how to master hundreds of solutions. And these developments can then only be successful if we can really provide the basis in terms of understanding and performance tests for users to have confidence in this solution. So we've got to really come with a game-changing approach that is based not solely on empirical testing, but on basic fundamental understanding, because this is going to be the only way to go faster. And you know, the kind of way we can imagine this is kind of an engineering approach, is to say, okay, we make multiple mixes, we alter the composition, the mixing, the temperature, etc., and then we measure all these things here, and then we set up empirical equations. I mean, many, many codes have these empirical equations relating strength at 1 year to strength at 28 days, etc. But if we have to do this experimental base over and over again, we're never going to develop, and we have to, I think, go through the fundamentals. As a material scientist, I express the fundamentals in terms of microstructure, but we can also think about this in terms of thermodynamics, in terms of kinetics. These are some of the things we're going to hear more about today in terms of, and modeling. Modern computer models can be very effective in bringing all of these together. And these processes we're talking about are nanoscale. And that's where we come to this word nanocem. You know, we're not trying to make nano cement with nano-sized grains. We're trying to generate nanoscience to enable development of macroscopic cement. And most of the things we're dealing with do come down to the nanoscale. We're, of course, very concerned with calcium silicate hydrate, which makes up about 50% by volume of all the concrete, all the cement paste, I should say, because we have the aggregate, of all the cement paste. We have processes involving chemicals like superplasticizers, which are the business of many of the additive companies. We have capillary forces acting on a scale less than 100 nanometers. These are all nanoscale processes, and this is what the word means. It's nanoscience of cementitious materials, not nanotechnology, because generally these things people are talking about in nanotechnology are high-cost, high-added-value solutions, and that's not really what we need in the field of construction materials, but we do need the kind of techniques and methodology they've developed in terms of nanoscience. So just to get to some of the facts and figures, these are very rough ideas. You know, we have probably 120 permanent research staff involved at any one time, at least 60-odd doctoral students. We have an overall contribution of industry that amounts to some $750,000 a year. But this really then gives us the leverage to bring in other projects. For example, we've had 2 European research networks financed to the tune of about $4 million each. And how we bring these together, we have what's called partner projects. So this is the individual research of the academic partners. First of all, we have to really see what are the interfaces, what are the connects. And only once we've done that through the forum of workshops, etc., do we identify where we need to have structuring projects, core projects, to bring this together. So the core projects, they are really aimed to bridge the gaps, and they typically fund 1 to 2 students, working across 2 to 4 institutions. And you will be able to see later, there's posters for all the core projects we've carried out over the years outside. So we now have 7 core projects that have been finished, and we have another 6 which are ongoing. And as I say, you can see more details of those later on. So the other presentations through the day are going to go into some details of this, and I hope what you will see is that with something like thermodynamics, this is a project that has evolved through several stages. It started as a core project, it was then developed further in these research training networks, and now is really out in the industry. So this is a sort of an example, an illustration of our method of working, starting with something at a quite fundamental level, but then evolving through several stages over even 10 years, all the time updating the knowledge base of the industry. I just want to finish by talking about our research training network, Transcend, which is just finished. And here again, we've got some very nice posters highlighting the contributions that have come out of that. These posters are particularly down in this corner here, where we've particularly highlighted in 3 areas, in CSH, in different levels, in absorption, in cracks, etc. What have been the findings of this project? We have the wrap-up meeting of this project yesterday. That doesn't mean everybody's finished, but this will be the last overall meeting. And this has been very, very exciting, because really here we've had a real network of projects linking together. So we started with 5 projects which focused on modeling type aspects, going from the molecular dynamics through Lattice-Boltzmann up to more macroscopic methods, interacting with experimental projects. I mean, modeling is totally sterile unless it's interfacing with experiments. And I think Paul will talk about this later on when we come to the subject of atomistic modeling. That this is going nowhere if you're just plugging numbers into a computer. You have to be going back and forth with experiments. And then we took this further of having a range of 4 projects where the students were actually out in the industry. This provides its own challenges, but nevertheless, there's a lot of interesting stuff comes out of here. I think in particular, you know, for me, it's very interesting to see this one that was done at Heidelberg, where the idea was to take a portable NMR unit, and this highlights that a lot of the kind of tests we're doing every day, a lot of the tests like absorption, are not working in at all the way we thought they were working for the last 50 years. And unless we really know how they're working, then we can't possibly design appropriate tests that can test this new range of materials. So, you know, I've just tried to give a few snapshots, and I hope during the day you're going to get more. Nanocem, for me, is really a complex, dynamic, and evolving research network. It's not something that's fixed today. It's as good as its partners, and it goes way beyond, you know, what any one person or what any small group of people can do. It finances core projects. It develops European projects. It provides an incredible training environment on many levels through formal courses, through knowledge transfer networks. And, you know, it's really all these different interactions that at the end of the day make the difference. In terms of the training, in terms of our Marie Curie networks, we've run 2 times a series of 6 courses. This is just some highlights of some of the topics that have been covered. From addressing the needs of industry, we've also run 4 knowledge transfer workshops, specifically targeted to the wider audience in the research labs of our industrial partners, to try and you know, give them a kind of a distillation of what is the latest thinking in different areas, and then numerous thematic workshops. So what we're trying to do with this, as I say, identify gaps, plan and fund collaborative research. In the research programs themselves, we're training new people. Many of the graduates of our core projects are now employed in the industry, and I think this then will make a very substantial contribution to better and more sustainable cementitious materials in the future. And I just want to finish with this slide from Meta. You know, I think this is where we were in 2000. You know, in my lab, I'm looking at the microstructure and I'm seeing this grey stuff. And over in Peter's lab, he's putting his stuff in the NMR and he's seeing this different grey stuff. And over in Meta's lab in Denmark at the time, she's seeing this grey stuff. And when we start to work together, well, we see it's grey stuff, but it has a lot more sense than we could ever have put to it by just working individually. So thank you there very much, and I hope you'll have an interesting day, and people will be able to ask your questions above and beyond the formal presentations. Thank you.